the quietest depths of space, some stars carry fields so intense that even emptiness seems to ripple. Tonight the journey moves through magnetars, through flare light, through the strange path from violent crustal stress to brief radio flashes that cross galaxies. If these calm science journeys help bring rest support, Space Dreams documentary with a like, subscribe and a gentle notification bell. New long-form episodes arrive regularly with slow visuals, steady pacing and deep cosmic scale. Now the darkness opens, the first signals begin. A magnetar begins as a simple shape in the dark, a small sphere whose influence reaches far beyond its surface. The defining feature is a magnetic field so intense that it becomes the first explanation for everything that follows. In that region, the field can be about 100 trillion times stronger than Earth's magnetic field, and the comparison is less a boast than a warning about scale. The star itself stays compact. The space around it does not. A slow scene forms around the object as faint thread-like arcs of light trace curved paths above the surface. The arcs do not sit still. They tighten near the star and loosen farther out. They sketch a geometry that cannot be touched yet still shapes every charged particle nearby. The early anchor settles quietly. Magnetars matter because a magnetic field of this strength stores energy in its structure, and that stored energy sometimes escapes in sudden bursts. The burst can be bright enough to stand out across the galaxy, even when the source remains a single unresolved point of light. A first small clarity arrives here. The flare is not a separate event dropped onto the star. It is a release from the same invisible architecture that holds the environment together. The boundary of that environment is not drawn by rock or gas, it is drawn by force. At a distance, the magnetar resembles a dark seed at the center of a translucent cocoon. The cocoon is the magnetosphere. Magnetosphere means a region where magnetic forces shape motion, and ordinary straight lines become curves. A simple image makes this easier to hold. Imagine a spiderweb stretched in still air with drifting dust carried past it. The dust does not choose to stop. It stops because the web offers paths and traps. In the magnetosphere, the web is made of field lines, and the dust is a thin haze of charged particles. The particles spiral as they move, and the spirals tighten where the field is stronger. Close to the star, the spirals shrink into narrow coils. Farther out, the coils widen into relaxed loops. The same motion repeats at every scale. A quiet payoff slips in. The magnetar does not need to throw material outward to change its surroundings. It only needs to rearrange the web because the web decides where energy can flow. The visual anchor deepens. Above the surface, bands of light appear as pale, ribbon-like curtains that wrap around the star's magnetic poles. The ribbons look layered. The inner edge is sharper. The outer edge is softer, fading through a gradient into darkness. Some patches brighten as if the web tightens. Other patches dim as if a strand slackens. Even when the star itself cannot be resolved, the timing of these changes carries structure. A pulse can arrive, then arrive again with a steadiness that hints at rotation. A flare can erupt, then fade into a slow afterglow that hints at trapped particles cooling. These are clues from light alone. The field cannot be seen directly. It leaves no outline in the vacuum. It only reveals itself through how radiation is guided, delayed, and filtered. Here the limit of observation appears without drama. At interstellar distances, the source collapses into a point, and the magnetosphere is far too small to image as a shape. Only changes in brightness, color, and timing survive the journey. Different arrangements of the web can produce similar signals, and the true geometry stays partly ambiguous. This is the first place where intuition can mislead as well. A magnetic field on Earth is familiar because compasses align and auroras glow. A magnetar field lives in a regime where familiar pictures stretch and tear. A gentle correction arrives. Magnetic strength is not only about pulling on metal, it is about controlling plasma-shaping radiation and storing energy in twisted structure. The story moves inward for a moment, but not to a human scale. The magnetar is a neutron star, a remnant so dense that a small change in the crust can matter across the whole surface. The crust is not a thin shell like ice over water. It is a rigid lattice under extreme pressure, and it sits on matter that behaves unlike ordinary solids or liquids. The magnetic field threads this crust. Over time, the field changes slowly. The change is not visible as motion of the star, it is visible as stress building in the lattice. A second small payoff arrives here. The flare can begin as a mechanical adjustment like a stiff surface finding a new equilibrium. A fracture or shift in the crust can jolt the field lines anchored to it. When field lines are forced into new shapes, the outer web responds. The response can be gradual. It can also be abrupt. The environment is a reservoir. It stores energy and twists like tension held in a woven net. A quiet scene returns to the outer region. A cluster of field lines arches outward and back, forming a loop that rises from one part of the surface and returns to another. The loop looks like a luminous handle against blackness. Along the handle, a thin glow brightens and dims as if a bead slides along an invisible thread. The bead is not a solid object. It is a packet of energetic particles trapped to the line. The packet spirals. The spiral produces radiation. The radiation escapes along directions set by the geometry. This is why the magnetosphere feels larger than the star. It is the stage where motion happens. It is also where the most dramatic releases can begin. A third small clarity settles. Giant flares are not only explosions of light, they are reorganizations of the web, and reorganizations change the pathways along which particles travel. A scale shift arrives softly. The particle spiral is microscopic, a tight helix traced in fractions of a second. The magnetosphere loop is enormous, stretching thousands of kilometers above a surface only tens of kilometers wide. Both are the same motion, under different magnifications. Another limit comes into view, this time a limit of explanation. The strongest fields push matter and light into regimes where equations become sensitive to unknown details of the interior. The exact state of the deepest layers remains uncertain, and that uncertainty leaks outward. A model may describe the web in broad strokes, yet fail to predict the precise moment a flare begins. The star can appear calm for long stretches, then change quickly. This is not a mystery held back for suspense. It is simply the nature of a system that stores tension quietly and releases it when a threshold is crossed. The threshold itself depends on details that are hidden behind distance and density. The section ends by widening the frame again. Around the magnetar space is not empty in the way a quiet night seems empty. It is a sparse medium that can be shaped, folded, and briefly lit by the star's field. This shaping is the first foundation for everything that follows, including the brief radio flashes that later appear like needle points of energy. Before those flashes can be approached, the space around the magnetar needs a clearer map. The next step is to move along the web itself from the star's surface, out to the boundary where the field loosens its grip. The space around a magnetar holds a shape that is felt rather than seen. That shape is the magnetosphere, a layered region where magnetic structure guides every charged particle. In that region, a simple boundary appears between tight control and loose drift. Close to the surface, motion clings to curved paths. Farther out, the same motion begins to slip and open. A slow visual forms as a dark sphere sits inside a faint translucent shell. The shell is not uniform. One side looks round and smooth. Another side narrows into a tapered cusp where lines seem to stretch outward. The edge is not a wall. It is a gradient where order weakens with distance. A small clarity settles early. The magnetosphere is not empty space with decoration. It is the main stage that decides whether energy stays trapped or escapes. The magnetosphere has closed regions and open regions. Closed field lines loop back to the star, and they act like corridors that return everything home. Open field lines reach outward, and they act like corridors that never return. A simple analogy holds the difference without strain. A bay with a narrow mouth keeps drifting foam circling inside. The open sea lets the same foam disperse and vanish. The magnetosphere behaves in the same way, but the foam is plasma, and the coastline is magnetic geometry. The first payoff arrives quietly. A flare does not need to throw matter far away to matter. It can change which corridors exist, and that alone changes what escapes. The visual anchor deepens with nested layers. Near the star, faint bands of glow gather into thin rings around the magnetic poles. The rings are not perfectly sharp. They brighten on their inner edge and fade outward as if the field strength falls like a slope. Between rings, darkness returns in clean gaps. The gaps are not holes in space. They are regions where fewer particles remain trapped long enough to glow. Motion becomes visible as a slow drift of brightness along the rings. A bright patch slides and thins. It then reappears on the opposite side like a tide that circles a basin. The physical detail matters here. The magnetosphere has gradients. It has layers. It has boundaries shaped by curves rather than surfaces. The second payoff arrives with a simple mechanical truth. Charged particles do not move straight in a strong magnetic field. They spiral around field lines as they travel. The spiral radius shrinks where the field is stronger. The spiral widens where the field is weaker. This single rule creates structure across vast scales. At one moment the spiral is microscopic, traced in a fraction of a second. At another moment the same particle follows a loop that rises thousands of kilometers above the star. The scale shift is gentle. The same motion exists from the smallest curl to the largest arch. A single number helps hold the size without turning the mind sharp. The closed region can extend to about 10 times the star's radius, like ripples, spreading 10 pebble widths from a dropped stone. The point is not precision. The point is that a small star can command a much larger volume. Another scene enters slowly. A thin stream of particles drifts outward along a line that does not return. The stream is faint at first. It becomes brighter where the line narrows. It becomes dimmer where the line fans out. The stream looks like a pale filament, and it flickers as if the supply is uneven. A third payoff arrives in that flicker. The magnetosphere can store energy by twisting its own structure, and a twist changes where filaments appear. Twist means field lines become wound and stressed. 2 sentences make it ordinary. A twisted cord holds tension even when nothing moves. A relaxed cord holds less tension even if it looks similar. This matters because stored tension can be released as radiation. The release does not require a violent outward blast of matter. It can be a rearrangement of curves that frees energy already present. The limit of intuition arrives here with a soft edge. On familiar scales, a magnetic field is imagined as a set of neat lines in clean space. In the magnetosphere, the field lives with plasma that is never perfectly still. The plasma pushes back. It carries currents that reshape the field. The picture becomes a coupled system rather than a fixed scaffold. This is where intuition based on rigid lines begins to fail. The limit of observation arrives as well, and it is practical. The magnetosphere is far too small and distant to be resolved as a shell with a cusp. Only the light that escapes can be measured. Timing spectrum and polarization hint at geometry, yet different geometries can produce similar signals. The true boundary is inferred indirectly, not traced directly. Even the brightest events can be reduced to a changing point of light. A quiet clarity follows from this constraint. Models are judged by whether they reproduce patterns, not by whether they match a photographed shape. The story continues with a second visual still slow and concrete. A loop of field lines rises from the surface and arches back down. Along the loop, a thin band of glow forms a ladder of brighter and dimmer segments. The segments drift as particles scatter and cool. The ladder is not fixed. It shifts along the curve like a ripple travelling through a stretched ribbon. The physical details remain grounded. The loop has curvature. The glow has a sharp inner boundary and a soft outer fade. The brightness changes along the arc as density changes. Another payoff arrives in the way the loop fades. Radiation does not leave the magnetosphere unchanged. It can be scattered and redirected by plasma. It can be delayed by passing through regions of different density. The signal that reaches far space carries the imprint of the path it took like a faint echo that reveals the shape of a corridor. The analogy is quiet and everyday. A sound in a cavern arrives with a softened edge and a stretched tail. The cavern is not seen. Its shape is learned from how the sound returns, in the same way the magnetosphere is learned from how light is shaped as it leaves. The scale shifts again without hurry. The corridor shaping the light is only thousands of kilometers across. The journey after that is light years of empty distance. The imprint survives both. The section settles toward a gentle transition. Once the magnetosphere is understood as corridors and boundaries, the next step is to add rhythm. Rotation introduces a steady sweep that turns geometry into pulses. The following section moves from static shape to moving pattern, and it does so without leaving the calm structure behind. A magnetosphere can look still until rotation adds a steady turning that repeats without hurry. The repeating pulses come from rotation sweeping a narrow emission region through space. In that region, magnetic structure and spin combine into a rhythm that can be measured as timing alone. A quiet visual begins close to the star. A pale, wedge-shaped glow lifts above one magnetic pole. It is not a solid beam. It is a thin region where radiation escapes more easily. The wedge has a bright inner edge and a softer outer fade. As the star turns, that wedge sweeps across the surrounding darkness. The sweep is smooth and patient. A first clarity arrives early. The pulse is not a heartbeat of the star's interior. It is a geometric sweep, and geometry can look like repetition. The rotation period of a magnetar is often about 5 seconds, like a slow blink that returns again and again. That number is not a limit. It is an anchor for pace. A few seconds is long enough for a glow to move across a loop of field lines. It is also short enough for a distance signal to build a pattern over minutes. The magnetosphere responds to rotation by arranging currents and charges into preferred lanes. Those lanes are not straight. They curve and twist. They form a rotating scaffold that carries the emission region around. The main analogy stays simple and natural. A striped seashell turns in shallow water, and a bright band passes the same rock again and again. The band is not a signal sent outward. It is a pattern revealed by rotation. In the same way, a magnetar reveals its rhythm by turning a structured emission region through space. A second visual arrives with more detail. The sweep passes over a thin veil of plasma that hangs in the outer magnetosphere. The veil is faint like a translucent sheet with ripples. Each time the wedge crosses it, a narrow crescent brightens along one fold. The crescent slides and fades. It leaves no permanent mark. It only shows where energy travels at that moment. A small payoff settles here. Rotation does not create energy by itself. Rotation decides where existing energy can escape, and when escape aligns with a distant direction. The word beam can mislead. It suggests a rigid shaft of light. In reality, the emission region can be a hollow cone or a fan. It can have uneven brightness across its width. Its edges can fray as plasma conditions shift. The physical detail matters. The edge is sharper where particles are more tightly guided. The edge is softer where scattering and density variations blur the boundary. Light behaves as a traveller in a corridor. It arrives cleanly when the corridor is narrow. It arrives smeared when the corridor widens. Another payoff follows the corridor idea. A regular pulse does not guarantee a perfectly stable source. It can be stable rotation combined with slowly changing corridors. The pulse profile can change while the period stays the same. A third visual slows the scene further. Near the star, a bundle of field lines arches upward. The bundle is brighter on its inner face. The outer face is dim like a shadowed side of a ribbon. As rotation continues, the ribbon seems to roll. Its bright face turns away. Its dim face turns toward the surrounding dark. The change looks like a slow breathing of light, yet it is only a change in viewing angle and scattering. The scale shifts gently. The ribbon is thousands of kilometers long. The star beneath it is only tens of kilometers across. The same rotation carries both. The next clarity arrives in a quiet step. If a pulse is seen, the emission region must cross the distant line of sight. If a pulse is not seen, the region may never cross it. This is a limit of observation that shapes the entire story. Magnetars can exist without being recognized as pulsing sources. The geometry can hide them, distance can hide them. Intervening plasma can hide them. Even when pulses are present, the beam shape is not directly imaged. It is inferred from timing and from how the pulse shape changes. The inference has limits. A narrow fan and a wide hollow cone can produce similar patterns. A patchy emission region can mimic a stable one. Timing noise can blur the picture as well. Rotation remains the clock, yet the hands of that clock are drawn in light that is filtered and scattered. A new visual holds on the far side of the magnetosphere. A boundary appears where field lines begin to open and stretch outward. Near that boundary, the sweep of the emission region becomes less uniform. The glow narrows into a thin blade, then widens. It is like a wavefront that changes thickness as it passes through layers of different density. A small payoff arrives from that thickness. The magnetosphere is not a perfect vacuum. It has gradients that can delay and spread radiation. The same pulse can arrive with a sharp front at one frequency and a softer front at another. The pulse can grow a tail as scattered paths add delayed copies. The corridor is not a single tunnel. It is a bundle of nearby paths. The bundle can diverge and rejoin. This makes the pulse a probe of structure, but only a partial probe. A limit of intuition appears here. A rotating star is often imagined as a rigid sphere turning in emptiness. A magnetar turns inside a field that carries energy and plasma. The rotation interacts with that plasma. Currents adjust. Charge densities shift. The emission region can drift slightly. That drift can look like a change in spin when measured from afar. It can also look like a change in beam shape. The system is coupled. The rotation is simple. The surroundings are not. Another payoff lands softly. A stable period can coexist with a changing pulse shape, and the change is a clue that the magnetosphere is alive with slow rearrangements. The analogy of the seashell band returns in a final refinement. The shell turns at a steady pace. The water above it can ripple. The ripples distort the band's appearance without changing the shell's rotation. In the same way, plasma variations can distort the pulse without changing the underlying clock. A final, visual anchor arrives to close the journey. The wedge of glow sweeps one last time across the outer veil. A bright crescent forms along a fold, then thins into a line, then fades into a smooth gradient. The darkness returns, the rhythm continues. The sense of repetition remains, yet the details never repeat exactly. The transition is gentle and direct. Once rotation sets the clock, the next step is to ask what can disturb the clock's surroundings. The following section moves inward to the crust, where stress can build and release into the magnetosphere as sudden change. A magnetar can seem steady until its surface carries stress that has nowhere to go. The crust stores that stress, and a sudden adjustment can feed energy into the magnetosphere. The scene begins close to the star where the surface appears matte and pale. A faint pattern spreads across it like a mosaic of plates. Each plate boundary is subtle. Some seams look darker, like thin shadows sunk into the crust. Near one magnetic pole, the seams tighten into a denser network. The second sentence settles the main idea early. The crust does not glow by choice. It glows when stored strain shifts into motion and heat. The first small clarity arrives here. The magnetosphere can twist slowly for years, but the crust can resist and hold the twist in place. This makes the surface a kind of anchor point. When the anchor slips, the outer field responds. The core concept stays simple and limited. The crust is a rigid lattice under extreme pressure. It behaves like a solid that can bend slightly then break. The magnetar's field threads this solid. The field changes slowly. The solid resists. A second concept enters as quietly as a ripple. A starquake is a sudden crustal adjustment that releases stored strain. Starquake means the crust shifts and cracks and energy moves outward. A simple analogy holds it without harshness. A sheet of cooling glaze on a rock can hold tension as it hardens. Fine cracks appear when the tension exceeds what the glaze can carry. The cracks do not add energy. They release energy that was already stored as strain. That matters because the release can be fast. It can push the magnetosphere into a new arrangement. A slow visual follows a single crack line. It begins as a hairline seam. It lengthens along a curved path. It branches into a fork. The branch edges look sharp on one side and feathered on the other as crushed material darkens the line. A small payoff arrives inside this image. The crack does not need to open wide to matter. Even a tiny shift can move the magnetic footpoints anchored in the crust. Footpoints means where magnetic lines attach to the surface. One sentence defines it. 2 sentences return to plain imagery. A loop of field lines is like a taut ribbon pinned at both ends. If one pin slides, the ribbon re-angles and tightens elsewhere. The 3rd sentence closes the loop. That re-angle changes where particles spiral and where radiation can escape. The story moves deeper by one layer but remains calm. Beneath the crust, matter is denser and more fluid-like in behaviour. The crust floats over it like a stiff skin over a heavy sea. The crust is not thin in an everyday sense. It can be about 1 kilometre thick, like the depth of a very deep lake. That single number gives a safe scale. The surface crack is small. The thickness beneath it is vast. The shift is local. The consequences can be global. The scale shift arrives gently here. A fracture measured in meters can influence a magnetosphere that reaches thousands of kilometers. Another visual anchor forms at the boundary between crust and magnetosphere. Above the cracked region, faint arcs brighten. The arcs curve upward and back. Their inner edge is bright and narrow. Their outer edge fades into a soft gradient. The bright edge looks like a thin strand pulled tight. The fade looks like mist thinning into darkness. A payoff settles into the contrast. The magnetosphere acts like a tensioned fabric. The crust acts like a stiff frame. A shift in the frame can change the fabric's tension pattern immediately. The next step stays within 2 concepts yet opens a mechanism. The crustal shift injects motion into magnetic structure. The structure can become twisted and stressed. The stress can then release by reconfiguring the field. This is not a separate concept. It is the consequence of the same anchoring. A new analogy carries that consequence without repeating earlier images. A braided vine held between 2 stones can be twisted slowly. The twist stores tension along the braid. If one stone slips, the braid snaps into a simpler shape. The release is not loud in vacuum. It is bright in radiation. Another visual holds on the outer loop as it responds. A loop that was rounded becomes slightly kinked. The kink forms a corner. The corner sharpens into a cusp. Along the cusp, brightness briefly intensifies like a thin seam of heat. The seam then spreads into a broader glow that fades outward. A small payoff arrives as the cusp softens. The flare is not only light, it is a change in geometry that redirects energy pathways. The timing of the change can be short. The consequences can linger as trapped particles cool. The limit of observation arrives softly and precisely. The crust cannot be seen directly at these distances. No surface crack is resolved as a line. Only the light and its timing are measured. A burst appears, an afterglow follows. The details of the fracture are inferred from patterns not photographed. This makes cause and effect uncertain in fine detail. A flare can suggest a quake. A quake can suggest a flare. Multiple internal arrangements can produce similar outward signals. Another limit of intuition arrives alongside it. A rigid crust suggests a simple break and a simple release. In reality, the crust can fail in patches. It can slip along several seams. It can transfer stress to a nearby region. The failure can be partial. The release can be staged. The outward signal can look like one event, yet it may be a sequence of micro shifts below visibility. Another visual anchor comes in slow motion. The surface mosaic seems to dim in one patch, then brighten in a neighbouring patch. The boundary between patches looks slightly raised like a ridge in relief. The ridge casts a thin shadow that changes as the region settles. Above it, the magnetospheric glow shifts position. A bright arc moves a small angle across the darkness. The move is subtle. The meaning is large. A payoff settles into that subtlety. The magnetosphere is anchored to the crust. Changing the anchor changes the map that guides particles. The map is made of curvature and gradients. It is redrawn by shifts that can be invisible at the surface. A gentle widening follows. Over long spans of time, the magnetic field itself decays and rearranges. That slow change keeps feeding stress into the crust. The crust is forced to keep adjusting. The adjustments can be rare. They can also come in clusters. The star can appear quiet for years. It can then show several outbursts close together. This is not a cliffhanger. It is the natural result of stress accumulation and release. A final visual anchor closes the section with calm. The cracked region cools. The bright arcs above it thin into faint threads. The threads lose their sharp inner edge and become a smooth haze. The haze fades into darkness that feels stable again. The transition stays soft and forward. Once crustal shifts can trigger magnetospheric change, the next step is to follow the magnetic structure itself. The following section moves outward to how the field stores tension and releases it as flares. A flare begins long before any light escapes in the quiet way magnetic structure stores tension. The magnetosphere behaves like a stressed configuration that can suddenly simplify and release energy. The scene opens on a wide loop above the magnetar, faint and curved against blackness. Along the loop, thin striations appear like parallel threads. The threads gather into a tighter bundle near the surface. Farther out, the bundle spreads into a fan. The edges of the fan fade through a soft gradient. The second sentence holds the early anchor. The flare is a rearrangement of magnetic shape and the light is a consequence. The first small clarity arrives here. Energy can be stored in the twist of field lines. It does not need motion that looks dramatic. Twist means field lines are wound and stressed. One sentence defines it. Two sentences return to ordinary imagery. A twisted rubber band holds energy even when held still. A relaxed rubber band holds less even if it looks similar at a glance. That matters because a magnetosphere can carry twist for a long time. It can release it quickly when a threshold is crossed. The main analogy stays quiet and unique. A tightly folded paper fan can hold a pattern in its creases. When the fold is released, the fan opens and the stored shape becomes a smooth curve. The opening is sudden. The result is simple. The magnetosphere does the same in its own language of curvature. A slow visual anchor forms around that idea. A region of field lines appears braided like several arcs pressed together. The braid is not a rope. It is a set of nearby curves carrying current. The inner side of the braid looks brighter. The outer side looks dim like a shadowed ridge. As the system changes, the braid loosens. The bright ridge shifts position along the loop. The dim side becomes less defined. A small payoff arrives as the braid relaxes. When the geometry simplifies pathways open for particles to accelerate and radiate, the light is not the cause. The light is the signature that a stored pattern has changed. A second concept enters, and it stays within the limit. Magnetic reconnection is the process where stressed field lines change partners and release energy. One short definition settles it. Reconnection means magnetic lines reconfigure and energy moves into particles and light. Two sentences make it concrete. Two curved ribbons can be pressed together until they snap into a new pairing. The snap is not heard. The snap is seen as a brief brightening along a seam. This matters because reconnection turns a slow build-up into a fast release. Another visual scene arrives to carry the seam. Near the top of a loop, a thin sheet of glowing plasma appears. The sheet is flatter than the loop itself. Its center is brighter. Its edges are softer. The sheet looks like a delicate veil stretched between two arcs. Along the center, a narrow line brightens as if heat concentrates there. The line is the reconnection layer. It is not wide. It is a boundary where magnetic direction changes rapidly across a small thickness. A payoff settles into that boundary. A thin layer can control a large volume because it is where the topology changes. Topology here means the connectivity of field lines. The magnetosphere can look similar before and after, yet the connectivity is different. That difference decides which regions trap particles and which regions vent them outward. A single number provides a gentle anchor for timescale. The bright spike of a flare can last about 1 second, like the quick flare of a match that is struck and then gone. The comparison is about duration, not heat. 1 second is brief. It is also long enough for light to travel hundreds of thousands of kilometers. The scale shift arrives quietly. A moment at the star becomes a moving shell of radiation that expands at the speed of light. The shell becomes larger than the magnetosphere within seconds, yet the origin remains confined to a region near the star. A second payoff follows that expansion. The flare is small in place and large in consequence. It can inject particles into the outer magnetosphere. It can alter the pulse profile that rotation reveals. It can leave an afterglow as trapped particles cool and scatter. A third visual anchor appears in the wake. After the brief spike, a softer glow hangs around the star. The glow forms a ring-like band around the magnetic equator. The band has a bright inner edge. It fades outward into darkness. Within the band, mottled patches drift slowly as if currents are settling into new lanes. The physical detail is steady and simple. There is curvature. There is layering. There is a gradient of brightness. Another payoff arrives in the fading. Afterglow implies confinement. If particles were free to escape immediately, the glow would vanish fast. A lingering glow suggests closed field lines that still trap motion. It suggests the magnetosphere has reconfigured into a new set of corridors. The limit of observation enters softly and clearly. At interstellar distance, the reconnection layer is not resolved. The sheet is not imaged. Only the light curve is measured, and the light curve is a blend of multiple processes. A sharp spike can come from rapid reconnection. A spike can also come from sudden opening of an emission corridor. A slower tail can come from cooling particles. It can also come from scattering in surrounding plasma. The data is timing and spectrum. The geometry is inferred. The inference has degeneracy, meaning different internal arrangements can fit the same outward signal. This is a boundary of certainty. Another limit of intuition follows. Reconnection is often imagined as two lines that touch and swap. In reality, the magnetosphere is three-dimensional. Many lines are involved. The release can be patchy. It can occur in multiple sites at once. The flare can look like a single flash, even if the process is distributed. The calm tone remains. These limits do not weaken the idea, they simply keep it honest. A final visual holds on the magnetosphere as it settles after the rearrangement. The braid that once looked tight now looks smoother. The reconnection sheet fades into a faint haze. The ring-like afterglow thins and breaks into softer patches. The patches drift along curved paths and gradually dim. The transition stays gentle and forward. Once reconnection can turn stored, twist into a flare, the next step is to see how extreme the brightest flares can become. The following section moves toward the largest releases, then returns to quiet afterglow. A giant flare arrives as a brief clearing of stored tension, and its brightness changes the surrounding space for a while. The event is a rapid magnetic reconfiguration that launches an intense spike, then leaves a longer fading tail. A slow scene opens in the outer magnetosphere where curved loops rise and return. The loops appear as faint arcs with a sharp inner edge and a softer outer haze. A narrow seam of light sits along one arc like a bright crease. The crease looks stable at first, it then tightens. The arc's curvature subtly changes and the bright seam slides toward the loop's highest point. A small clarity settles early. The spike begins where a large volume of stressed field finds a simpler shape, and the light marks that simplification. The first payoff arrives in the simplest rule. A stronger twist can store more energy, and a larger region can release more at once. A single release does not need a long build-up that looks active. It can come from a long, quiet accumulation. The visual anchor deepens as the seam brightens into a compact white hot patch. The patch is not a point. It has a thin boundary that looks crisp on one side and feathered on the other. The feathering is a gradient where particles scatter and thin. Around the patch, the magnetosphere briefly looks layered with an inner bright shell and a dimmer outer shell. The shells expand outward as a wave of disturbance. The wave has a sharp leading edge like a clean cut. Behind it, a trailing haze follows like mist. The main number lands gently on timescale. The initial spike can last about half a second, like the brief interval between two drops slipping from a heavy leaf. Half a second is short. It's also long enough for light to cross a distance larger than many planetary orbits. The scale shift arrives without force. The origin stays close to a star-sized object. The consequence becomes a moving shell that grows to millions of kilometers across in moments. A second payoff arrives in what follows the spike. The event does not end when the brightest light fades. A trapped region of hot plasma can remain tied to closed field lines. It glows more softly and more steadily. The glow can pulse with the star's rotation, yet the overall brightness declines. The concept stays limited and clear. A trapped fireball is a hot, confined plasma region held by magnetic geometry. One sentence defines it. 2 sentences return to imagery. It is like a pocket of glowing fog caught inside a ring-shaped bowl of invisible walls. The fog cannot flow straight out. It drifts along curved lanes and slowly cools. This matters because the fading tail carries information about confinement. The visual anchor shifts to the tail. Around the magnetar, a broad luminous band forms around the magnetic equator. The band looks like a faint halo with a bright inner rim and a soft outer fade. Within the halo, darker lanes appear like shadows running along the curve. The shadows are not objects. They are regions with fewer trapped particles. They change position as currents settle. A small payoff arrives inside the shadows. The tail is not just cooling. It is a reorganizing magnetosphere, and the organization shows up as moving contrast. The scene moves closer again but remains calm. Near the surface field lines crowd together. The crowding creates steep gradients. Where gradients steepen, energy conversion becomes more efficient. This is why the brightest part can be compact. It is also why the halo can be large. The compact region acts like a hinge. The large region acts like the door that swings. The main analogy stays unique and quiet. A pine cone can hold its scales tightly closed in dry air. When conditions change, the scales loosen and the cone opens into a simpler shape. The opening is a change in geometry, and it reveals what was stored in structure. A giant flare is not a pine cone. The analogy only carries the idea that shape can hold tension, and a new shape can release it quickly. Another visual anchor arrives as the disturbance travels outward. A thin wavefront moves through the surrounding plasma. The front is bright and narrow. Behind it, the glow becomes mottled and uneven. The mottling looks like gentle marbling with brighter streaks and darker pools. The streaks curve around the magnetar's axis. The pools gather near the boundary where closed lines become open. A payoff settles into this boundary. A giant flare can temporarily push the boundary outward, and then the boundary relaxes back. This changes what escapes and what stays trapped. The difference shapes both the spike and the tail. The limit of observation enters softly and precisely. At large distance, the earliest part of the spike can be too intense to be recorded with full detail. The true peak can exceed what measurement methods can track cleanly. The result can be a clipped profile where only a lower bound is known. Distance adds another blur. Scattering in intervening plasma can stretch the spike's trailing edge, and the tail can blend into background emission. This makes it difficult to separate what happens near the star from what happens along the path. Another limit of intuition follows. A flare suggests a simple explosion, yet the event is a sequence of geometric changes in 3 dimensions. Many field bundles can shift in rapid succession. The outward light can look like one flash even when the internal rearrangement is patchy. This does not reduce the reality of the event. It only sets a boundary on what can be inferred from light alone. A final scene settles the aftermath. The halo thins and becomes more transparent. The sharp inner rim softens into a smooth gradient. The mottled marbling fades until only a faint even glow remains. The glow continues to pulse with rotation, yet each pulse is slightly dimmer. The magnetosphere returns to a quieter pattern, with fewer tight creases and fewer bright seams. The transition remains gentle, with giant flares established as extreme releases. The next step is to approach what they do to light itself in the strongest fields, where familiar behaviour begins to bend. In the strongest magnetic regions, even empty space begins to behave like a subtle optical material. The key change is that light passing through the magnetosphere can be filtered and reshaped by the field itself. A slow scene opens close to the magnetar where darkness looks clean, yet faint radiation forms a thin curved sheet above the surface. The sheet is brighter along one edge. It fades along the other edge into a soft gradient. The boundary looks like a shoreline of light that does not touch any solid coast. A quiet anchor settles immediately. The field does not need to add new light to change a signal. It can change how existing light travels and what kind of light escapes. The first small clarity arrives in a simple idea. Light is more than brightness. Light carries orientation in its electric vibration. Polarization means a preferred vibration direction in light. One sentence defines it. 2 sentences return to ordinary imagery. A stream can carry floating leaves in many directions. A narrow channel can align those leaves into a common flow. This matters because alignment can be changed by the magnetosphere, and the change can be detected in the light. A second concept enters, and it stays within the limit. Vacuum birefringence is empty space, acting like 2 different transparent paths. 1 sentence defines it. 2 sentences make it concrete without any harshness. A clear mineral can split a single beam into 2 slightly separated rays. The rays travel together yet carry different orientations. This matters because a magnetar field can make the vacuum act like that mineral even when no material is present. A visual anchor forms around the magnetar as if a single glow is gently combed into order. Near the surface, radiation emerges from a hot patch. It spreads outward as a soft fan. As it moves through the field, the fan begins to look stratified. 2 faint ribbons appear within it, almost overlapping. One ribbon is slightly brighter at the inner edge. The other ribbon is slightly smoother and more diffuse. The separation is not wide. It is a subtle double structure inside one glow. A payoff settles inside that subtlety. The magnetosphere can imprint a signature on light without leaving a visible trace of itself. The signature is in orientation rather than in shape alone. Another scene arrives at a slightly larger distance. A curved loop of field lines rises and returns. Along the loop, a dim halo forms like a veil. The veil is brightest along a narrow arc. It fades on both sides. The fade is not symmetrical. One side looks sharper as if the corridor is well defined. The other side looks smeared as if scattered paths add a soft blur. The physical detail stays clear. There is curvature in the arc. There is layering in the halo. There is a gradient where the veil dissolves into darkness. A small payoff arrives as the smear becomes meaningful. Scattering and filtering are not separate decorations. They decide whether the signal stays crisp or becomes stretched. A brief flare can look longer if many slightly delayed paths contribute. A steady glow can look uneven if the filter changes with position. At this distance, light behaves as a traveller moving through a medium made of field and plasma together. The field sets the preferred directions. The plasma adds density variations that bend, delay and scatter. The combined effect can act like a soft prism and a soft diffuser at the same time. The main analogy stays natural and unique. Thin ice crystals high in a cold cloud can align in a preferred direction. A distant glow passing through the cloud can become partially polarized and softened. The cloud is nearly invisible. The change appears in the light. In the magnetosphere, the aligned structure is magnetic rather than crystalline. The idea is the same. Order in the path makes order in the signal. A gentle number anchors timescale without sharpening the tone. Light can cross the near magnetosphere in about 1/10 of a second, like the brief pause between two small wavelets on a quiet shore. This is short. It is also long enough for fast changes near the star to be carried outward as a recognizable pattern. The scale shift arrives without pressure. Inside 1/10 of a second, the change is local and compact. Over years, the same region can slowly evolve as the field relaxes and stress accumulates again. The same corridor can be stable in one moment and different in the next. A new visual anchor forms around an afterglow. A soft ring-like band appears around the magnetic equator. The band has a bright inner rim and a dim outer haze. Within the band, faint striations run along the curve like gentle brush marks. The marks drift and fade as particles cool. As the glow passes through the field, the inner rim becomes cleaner in one orientation and softer in another. The effect is not seen as two images. It is seen as a change in how sharpness and brightness relate to orientation. A payoff settles into that relationship. The strongest fields can make the vacuum act like a selector. It favors certain orientations over others. That makes polarization a key clue to conditions that cannot be seen directly. The limit of observation arrives softly and clearly. Polarization is hard to measure from a distant point source. The signal is often faint. Intervening plasma between source and far space can rotate and scramble orientation. Scattering along the path can dilute the imprint. Even when a polarization pattern is detected, more than one geometry can produce it. A loop-shaped magnetosphere and a more complex patchy structure can yield similar outward signatures. The inference depends on models and on incomplete information about the intervening medium. This is a limit of measurement sensitivity and a limit of indirect reasoning, not a lack of structure at the source. A second limit follows, and it is a limit of intuition. Vacuum is commonly imagined as nothing. In these conditions, vacuum is not nothing in its optical behavior. It becomes a faintly anisotropic medium, meaning it treats different orientations differently. This is not a dramatic change like a wall appearing in space. It is a gentle bias that accumulates along a path. A small payoff arrives in that accumulation. A tiny effect per unit distance can become meaningful across a long corridor of curved field lines. The magnetosphere becomes a quiet lens that shapes the signal's fine texture. Another scene closes in on the boundary where closed field lines transition toward open ones. The glow near that boundary looks torn into wisps. The wisps are thinner than the inner halo. They curve outward and then vanish. Their edges are ragged as if the corridor is less stable. The raggedness is a physical detail tied to density and field gradients. The payoff is immediate. Where corridors are less stable, the imprint on light becomes less predictable. The signal can become more variable in time and more complex in its polarization. The section ends with a calm widening. These optical effects do not stand alone. They sit on top of flares and afterglows and pulsing geometry. They quietly alter what escapes and how it arrives across interstellar distance. The next step is to carry this altered light into the briefest signals, where a moment of emission becomes a sharp radio flash, shaped by every layer it crosses. A fast radio burst appears like a single clean stroke across darkness, and then it is gone. The core reality is that a very short radio flash can carry information about both its origin and the space it crosses. A slow visual begins not with the burst itself, but with the corridor it must travel. A thin, dim haze surrounds the magnetar. It looks like a faint veil with uneven thickness. Some parts are almost transparent. Other parts gather into soft patches like mist clinging to curved magnetic loops. The veil has edges that blur into darkness. It also has sharper folds where density changes quickly. The second sentence sets the early anchor. The burst is short in time yet long in consequence because every layer it crosses reshapes it. The first small clarity arrives with a gentle correction. A fast radio burst is not a continuous beam. It is a brief packet of radio waves that leaves travels and spreads. The packet begins compact. It becomes a growing shell as it moves outward. The shell is thin at first. It gradually thickens as different paths add tiny delays. A single number anchors the timescale without strain. The burst can last about 1/1000th of a second, like the brief touch of a raindrop on still water before the first ring spreads. The comparison is about brevity and delicacy. 1/1000th of a second is so short that any change along the path matters. The first concept stays simple and limited. Dispersion is the frequency-dependent delay caused by plasma. One sentence defines it. Dispersion means lower radio frequencies arrive later through plasma. 2 sentences return to imagery. A ripple on a pond spreads with a front and a tail when the water is thick with floating debris. The front reaches first, the tail follows because the path is slowed unevenly. This matters because the burst becomes a record of the plasma it traverses. A visual anchor forms as the burst leaves the magnetosphere. A thin arc of radio emission emerges along an open field corridor. It is not seen as light. It is imagined as a shell moving outward. The shell crosses the boundary where closed loops end and open lines begin. At that boundary, the shell's leading edge stays sharp for a moment. Then it begins to fray. The fraying looks like a softening of the edge, like ink bleeding slightly into paper. The physical detail is the edge itself. It goes from crisp to blurred. That change is the first clue that the corridor is not uniform. A small payoff arrives inside the fray. The burst is not only a message from the source, it is also a scan of the medium. The burst then moves into the wider surroundings. A second visual scene appears as the shell passes through a filament of denser plasma. The filament is long and narrow like a faint thread stretched across space. As the shell crosses it, the burst is scattered. Scattering means radio waves take many slightly different paths. 1 sentence defines it. 2 sentences return to imagery. A flashlight beam through fog becomes a glow rather than a sharp spot. The glow arrives with a soft halo because some light takes longer paths. This matters because scattering broadens the burst in time. It adds a tail. It can also blur fine structure. The main analogy stays unique and calm. A single bell tap in a large cavern produces a sharp strike and a lingering soft decay. The cavern does not create the tap. The cavern shapes how the tap is heard. In the same way, the burst is shaped by every cavity and corridor in plasma it crosses. Another payoff settles into that analogy. A burst that looks longer may not be emitted longer. It may simply be smeared by the medium. A burst that looks clean may be a path through a quieter region. A third visual anchor forms farther out in interstellar space. The shell now spans a vast area. It is thin compared to its radius. The leading edge remains a boundary that expands smoothly. Behind it, a faint trailing layer grows fed by scattered paths and dispersed delays. The layer has a gradient. It is brighter near the front. It fades backward into darkness. The scale shift arrives softly here. The emission begins near a magnetar-sized object. Within seconds, the shell is larger than a star system. Within years of travel, it crosses the space between stars. Yet the imprint of 1/1000th of a second remains embedded in the wave train. Another small payoff arrives in this persistence. Time structure can survive immense distance when the medium is thin enough. This is why a brief radio flash can be detected across the universe. A limit of observation enters gently and precisely. The burst is too short to allow direct imaging of its source region. The origin is inferred from timing spectrum and polarization. Many mechanisms can create short bursts in principle, and different models can fit the same observed pulse shape. The medium adds additional uncertainty. Plasma near the source, plasma in the host environment, and plasma between galaxies all contribute to dispersion and scattering. Separating these contributions requires assumptions. Those assumptions can be wrong. This is a limit of indirect reasoning and a limit of incomplete knowledge of the path. A limit of intuition appears alongside it. A single burst feels like a singular event. In reality, the observed burst is the sum of many frequencies arriving at slightly different times. What appears as a single spike is a layered arrival. The layers can be hidden inside the envelope. Fine structure may exist below measurement resolution. The mind expects a single sharp click. The universe delivers a stack of near clicks that blend. Another visual scene holds on the burst as it's received far away, imagined as a curve of intensity over time. The curve rises sharply, it peaks, it then trails off into a smooth tail. The tail is not noise, it is structured smearing. The peak is not pure either. It can be clipped and distorted by limited sensitivity. The edges of the curve can be softened by scattering. The center can be split into sub-peaks that merge. A payoff settles in that curve. Even without seeing the source, the shape reveals whether the path is clean or turbulent. It reveals whether the medium has sharp density gradients. It reveals whether multiple corridors contribute. The story returns to the magnetar corridor for one last calm step. Near the star open field lines act like channels that can launch radio emission in brief packets. A change in magnetic structure can make a packet more likely. A flare can provide energy and motion. A quieter change can also do it. The section ends with a gentle transition. With dispersion and scattering in place, the next step is to connect these short radio flashes to magnetar processes more directly, and to see how a crustal shift or magnetic reconnection could ignite a burst in the first place. A fast radio burst can look like a sudden spark in the radio band, yet its origin can be a calm mechanical change in magnetic structure. The most direct link is that a magnetar's shifting field can create a brief coherent radio flash. A slow scene opens along an open magnetic corridor. The corridor rises from the surface as a curved bundle that narrows near its base and widens outward. Along its center, a faint thread of plasma becomes denser, like a translucent cord with a brighter core. The cord has a sharp inner boundary. It fades outward into a soft haze. The second sentence holds the early anchor. A short radio flash can be made when charges move in step, and magnetar conditions can briefly allow that step. The first small clarity arrives in a simple distinction. Ordinary emission is messy and adds up from many particles acting independently. Coherent emission is ordered and adds up from many particles acting together. Coherent means waves add in phase, so the signal becomes much stronger. Two sentences return to imagery. A crowd clapping at random creates a soft wash of sound. A crowd clapping in unison creates a single sharp crack that travels far. This matters because a fast radio burst requires that kind of unison in the radio band, even if it lasts only a moment. A second concept enters and stays within the limit. A charge bunch is a temporary packet of charges moving together along a field line. One sentence defines it. Two sentences keep it physical. The packet is like a thin bead sliding along a curved wire. The bead is not solid. It is a denser region in a flowing stream. This matters because a moving bunch can radiate strongly at radio frequencies when conditions are right. The visual anchor deepens as the corridor becomes active. Near the base of the bundle, a kink appears in the magnetic geometry. The kink is a sharp change in curvature, like a bend in a ribbon that was smooth a moment earlier. Along the kink, the plasma thread brightens. It tightens into a narrower filament. The filament then sheds a small knot that begins to move outward along the open line. The knot is the charge bunch. Its leading edge is sharp, its trailing edge is softer, fading into the filament behind it. A payoff settles into the shape. A brief change in curvature can form a bunch, and a bunch can form a burst. The burst is not a separate miracle. It is the radio signature of an ordered packet launched into a corridor. A single number anchors the timing in an everyday way. The ordered phase can last about 1/1000th of a second, like the instant a droplet separates cleanly from a thin stream before the stream reconnects. The comparison is gentle and about brevity. In that tiny interval, the bunch travels only a small distance near the star. Yet the radio wave train it produces begins a journey that can last billions of years across the universe. The scale shift arrives without urgency. A moment near the surface becomes a signal that crosses intergalactic space. Another visual scene follows the radio packet as it leaves the near magnetosphere. The emission region is not a fixed point. It is a short segment along the corridor where the bunch is most compact. That segment behaves like a moving window. As the bunch advances, the window advances with it. The radiation leaves in a narrow cone around the local direction of motion. The cone edge is not perfectly sharp. It has a gradient where emission weakens. That gradient matters because it allows small changes in geometry to change what is seen at a distance. A payoff settles into that gradient. A small shift in the corridor can turn a burst on or off for a distant direction without changing the underlying engine. The story then connects the burst to magnetar activity without adding new concepts. A flare or a crustal adjustment can disturb the magnetosphere. The disturbance can steepen electric fields along some lines. The steepening can bunch charges. The bunching can become coherent emission for a brief time. The chain is short and calm. It begins with geometry. It ends with a radio flash. A second payoff arrives here. A burst does not require the most violent flare. It requires the right corridor and the right brief ordering. That ordering can occur during a flare. It can also occur during a quieter rearrangement that barely changes high-energy light. A new visual anchor appears in the wake of a disturbance. A faint ring-like band forms around the magnetar. The band is not the burst. It is a region of elevated plasma density after a previous event. The band has a bright inner rim and a dim outer haze. Inside it, thin striations run like soft brush marks along the curve. As an open corridor passes through this band, the corridor's plasma thread becomes patchy. Dense knots form more easily where the band is thicker. A payoff settles into this environment. The magnetar can prepare its own conditions by leaving behind structured plasma, and that structure can make later bursts more likely. The limit of observation arrives softly and precisely. The radio burst is detected as a time series from a point source. The emission region cannot be imaged. The bunch cannot be seen. Even the corridor geometry is inferred. Multiple mechanisms can produce coherent radio emission in theory, and different models can match the same burst shape. The surrounding medium also reshapes the burst through dispersion and scattering. Untangling source physics from propagation effects is difficult. This is a limit of resolution and a limit of indirect inference, not a lack of physical process. Another limit of intuition follows. Coherence suggests perfect order, yet the order can be partial and short-lived. The bunch may fragment. Several small bunches may occur in sequence. Their signals can overlap and appear as a single burst. The mind wants a single switch that flips. The magnetosphere may provide a brief patchy phase of alignment instead. Another visual scene holds on a sequence of knots along one corridor. The knots are spaced unevenly. Each knot brightens and then fades as it moves outward. The first knot produces the main burst. The later knots produce faint substructure that may be smeared by propagation. The corridor itself begins to relax. The kink smooths into a gentler curve. The plasma thread becomes more uniform. The brief ordering ends. A payoff settles into the ending. The burst is the moment when ordering exists. When the ordering disappears, the same corridor returns to quieter emission. The transition remains soft and forward. With a plausible chain from magnetic disturbance to coherent radio flash, the next step is to test the link against patterns in repeating bursts where similar corridors may activate again and again under slowly changing magnetospheric conditions. A repeating fast radio burst feels like a quiet metronome that sometimes returns and sometimes stays silent. The simplest explanation is that the engine can remain the same while the corridor conditions switch between open and closed. A slow scene opens around the magnetar's outer boundary, where open lines begin to dominate. The boundary is not sharp. It looks like a dim shell with a bright inner rim and a softer outer fade. Along one quadrant, a wedge-shaped notch appears where the shell thins. The notch is a region of lower plasma density. Its edge is sharper on the inner side. Its outer edge dissolves into haze. The second sentence anchors the idea early. Repetition does not require a new source each time. It can come from the same source returning to the same temporary alignment. The first small clarity arrives in a gentle rule. A fast radio burst needs ordering, and ordering is easier when the plasma environment is calm and structured. When the environment is too dense or too turbulent, ordering is smeared before it can radiate cleanly. This is why the same magnetar can appear active for a while, then quiet. The key concept stays limited. Activity window means a span of time when bursts are more likely. One sentence defines it. Two sentences return to imagery. A lighthouse beam can be steady, yet fog can hide it for hours and reveal it for minutes. The lighthouse does not change. The air does. This matters because a burst can be present at the source yet absent in detection when the corridor is not transparent. A visual anchor forms inside the notch. A thin plasma thread runs outward along an open line. The thread is not uniform. It has beads of higher density spaced unevenly. Each bead has a crisp front and a softer trailing tail. The tails overlap slightly and create a faint layered gradient behind the beads. The beads drift outward. Some merge into larger knots. Some dissolve into haze. A payoff settles into that motion. Repetition can come from repeated formation of charge bunches along the same favoured corridor. The favoured corridor is not a rigid pipe. It is a path that becomes preferred when geometry and density align. A second concept enters and stays within the limit. Magnetospheric gating means the magnetosphere alternates between allowing and suppressing radio escape. One sentence defines it. Two sentences make it physical. A doorway with a hanging curtain can sometimes part and sometimes press together. Air currents and small shifts decide whether the passage is open. This matters because a burst can be produced yet not escape cleanly if the gate is closed. The main analogy stays unique and quiet. A wind chime can have many identical tubes, yet only certain gust directions produce a clear sequence of tones. The chime stays the same. The gust pattern decides which tubes ring and when. In the same way, the magnetar's field stays strong. Small changes in plasma distribution decide which corridors emit coherent radio and which corridors stay quiet. A single number anchors the cadence without tension. A repeating source can show active episodes lasting about a day, like a tide that returns and recedes over the span of a daylight cycle. The comparison is about episodic rhythm, not about water. One day is long compared with a burst. It is short compared with magnetic evolution. The scale shift arrives softly. The burst lasts about 1/1000th of a second. The active window can span many hours. The magnetar's field evolves over years and longer. Within that layered time, repetition becomes natural. Another visual scene slows the idea into geometry. The magnetar rotates. The favoured corridor sweeps around. Most of the time the corridor points away from the direction where a burst would be noticed at great distance. For a fraction of the rotation the corridor aligns. In that alignment the gating notch also matters. If the notch is present, the burst escapes cleanly. If the notch is filled with denser plasma, the burst is smeared and effectively erased. A payoff settles into this two-step filter. Repetition can be a combination of alignment and transparency, not only a sequence of identical emission events. The physical detail remains concrete. The notch has a sharp inner boundary and a diffuse outer edge. The plasma has beads and tails. The corridor has curvature that changes slightly with magnetospheric stress. The third visual anchor forms after a modest magnetic disturbance. The outer shell briefly thickens, the notch narrows, the plasma beads become more numerous and more chaotic. The corridor's glow becomes mottled like marbling. In that interval, bursts become harder to produce coherently. After the disturbance settles, the shell thins again. The notch returns. The beads become fewer and more orderly. A payoff arrives in that settling. The magnetosphere can self-regulate. It can shift into a state where coherent emission is possible, then drift out of that state as plasma accumulates. The limit of observation arrives softly and precisely. A repeating pattern in detection does not directly reveal a repeating pattern at the source. Missed bursts can occur because of sensitivity limits. Small bursts can fall below detection threshold. Scattering can smear a burst into the background. Dispersion can stretch it across time bins. In addition, a burst can be produced in a corridor that does not align with the distant line of sight. The source can be active while appearing quiet. This is a limit of sampling and a limit of geometric selection. Another limit of intuition follows. Repetition can suggest a regular clock, yet the cadence can be irregular because gating depends on a changing environment. Plasma density can vary. Currents can drift. Small magnetic rearrangements can alter which corridor is favoured. This produces clusters, pauses, and uneven spacing. The mind expects a tidy schedule. The magnetosphere provides a shifting set of conditions. Another payoff settles into that mismatch. Irregular repetition can still come from a single engine, because the conditions for coherence are narrow and move in time. A final visual anchor closes the section with calm. The boundary shell becomes nearly transparent again. The notch is visible as a thinning in the haze. Along one corridor, a new bead forms with a crisp front and a soft tail. It slides outward. For a brief alignment, a clean radio flash would depart. The corridor then turns away. The shell remains. The system returns to quiet. The transition stays soft and forward, with repetition framed as gating and corridor selection. The next step is to widen the view to what the burst collects on its long journey, and how the intervening medium leaves fingerprints that help separate source behavior from propagation. A fast radio burst carries a hidden map of the space it crosses even when its source remains unseen. The clearest map comes from how different radio tones arrive at slightly different times. A slow scene opens on the burst as a thin wavefront moving outward imagined as a transparent shell. The shell is crisp at its leading edge. Behind it, a faint trailing layer follows like a soft fog. The shell passes through a region of interstellar plasma that is not uniform. The plasma forms long filaments and low-density cavities. The filaments look like faint threads. The cavities look like clearer lanes. The shell's leading edge stays sharp through a cavity. It thickens as it crosses a filament. The second sentence anchors the idea early. The burst becomes stretched in time by the medium and the stretch can be measured. The first concept stays simple and limited. Dispersion is the frequency-dependent delay caused by plasma. Dispersion means lower radio frequencies arrive later than higher ones. Two sentences return to imagery. A thin sheet sliding over a rug slows where the rug is thicker. The front stays crisp on smooth floor. It lags and ruckles on a rough patch. This matters because the delay pattern reveals the total amount of plasma along the path. A small payoff arrives quickly. The burst is not only a signal, it is a probe of invisible matter that does not shine. The visual anchor deepens as the shell passes into a denser pocket. The pocket is shaped like a flattened lens. Its boundary is sharper on the near side and softer on the far side. Inside, the density has a gradient. It is higher at the center and lower at the edges. As the shell crosses it, the burst is dispersed more strongly. The low tones fall behind. The high tones stay nearer the front. The result is a slanted arrival in time. Another payoff settles into the slant. Measuring the slant yields a single number called a dispersion measure, meaning the integrated electron density along the path. One sentence defines the term. Two sentences keep it plain. It is like counting how much mist is stacked along a long road. Thick mist for a short stretch can equal thin mist for a long stretch. This matters because the same number can come from different distributions of plasma, and that ambiguity must be carried gently. A single number anchors the scale of delay. The lowest tones can arrive about 1 second after the highest tones, like a slow echo following a sharp clap. 1 second is long compared with the burst duration. It is short compared with travel time across space. The scale shift arrives softly. 1/1000th of a second at emission becomes a spread of about a second at arrival. The same signal then continues onward across many millions of years of travel. The burst is brief, its journey is vast. A second concept enters and stays within the limit. Scattering is the multipath broadening caused by small-scale turbulence. One sentence defines it. 2 sentences return to imagery. Light through frosted glass spreads into a soft patch. The patch has a bright core and a fading halo. This matters because scattering adds a tail to the burst, and the tail suggests fine structure in the plasma. A visual anchor forms around that tail. The time profile rises sharply, and then trails away smoothly. The trailing edge is not a straight line. It is curved with a gentle bend that fades into background. The curvature suggests many slightly delayed paths. The burst is a bundle of arrivals rather than a single arrival. The physical detail is the tail itself. It has a bright ridge close to the peak. It has a soft gradient that declines. It sometimes shows faint ripples within the tail like subtle striations. A payoff settles into those striations. The tail can hint at how turbulent the path is and where the turbulence might lie. Strong scattering often points to dense, uneven regions near the source or in a host environment. Weak scattering suggests a cleaner corridor through interstellar space. The story then widens to the host environment without adding new core concepts. A burst can pass through a local nebula. It can pass through a star-forming region. It can pass through a calmer halo. Each layer adds dispersion and scattering. The total is measured. The division among layers is inferred. This is where the map becomes useful and limited at once. The limit of observation arrives softly and clearly. Dispersion measure gives an integrated quantity. It does not directly reveal where along the path the plasma sits. A dense pocket near the source and a diffuse medium over a great distance can yield similar totals. Scattering helps, but is also ambiguous. Scattering depends on turbulence, not only density. 2 paths with equal density can scatter differently if one is smoother. Inference depends on models of plasma distribution. Those models have uncertainties. This is a limit of indirect reconstruction. It is also a limit of measurement bandwidth and signal to noise, since small features can be lost. A limit of intuition follows. A map suggests a clear picture with boundaries. In reality, the plasma is a web of gradients and filaments. There are no clean walls. The burst samples it along one narrow line. That line is not the whole medium. It is one thread through a complex tapestry. Another payoff settles into that humility. Even a partial sample is valuable because many bursts through many directions can build a statistical picture of cosmic plasma. The visual anchor shifts to a wider scale. The burst shell leaves a galaxy and travels through intergalactic space. The medium there is thinner. It is still structured. It forms faint sheets and long strands between galaxies. The shell crosses a strand. The strand thickens the dispersion. It can also add a small scattering tail. The effect is subtle per unit distance. It accumulates over enormous length. This is another gentle scale shift. Small delays add up across millions of light years. The burst arrives with a fingerprint of the cosmic web. A final scene closes the section with calm. The time profile is imagined as a thin line drawn in light. The line tilts because of dispersion. It grows a soft tail because of scattering. The tilt and tail remain even after the burst has passed. They remain as measurable traces in the received wave train. The transition stays soft and forward. With the propagation fingerprints in place, the next step is to return to the source environment and ask what makes some bursts repeat in distinctive patterns, and how local plasma and magnetic geometry together create those patterns. A magnetar can influence its surroundings long after any single flare fades through a steady outflow in a changing magnetic envelope. The environment becomes a stage where later signals are filtered, delayed, and sometimes enabled. A slow scene opens around the magnetar, a distance where the near magnetosphere gives way to a wider bubble of plasma. The bubble is not a perfect sphere. It is slightly squashed along one axis. Its edge is a thin, bright arc on one side and a softer haze on the other. Along the edge, faint ripples appear like shallow waves on a boundary. The ripples mark a pressure balance where outward flow meets surrounding material. The second sentence holds the early anchor. The surrounding medium is not passive. It can be shaped into a nebula-like cavity that affects radio bursts and afterglows. The first small clarity arrives in a calm rule. A strong magnetic object can drive a wind, and a wind can inflate a bubble. The bubble then becomes a reservoir of plasma and turbulence. That reservoir can thicken the path for radio waves. It can also provide structured corridors that make repetition easier. The first concept stays limited. A magnetar wind nebula is a bubble of magnetized plasma around the star. One sentence defines it. Two sentences return to imagery. A steady stream of warm air can inflate a thin balloon inside a cooler room. The balloon's skin forms a boundary. Inside, the air is warmer and more active than outside. This matters because a radio burst crossing the bubble collects dispersion and scattering from its interior. A visual anchor forms at the boundary. The shell looks layered. There is a bright inner rim. There is a dim outer skirt that fades into darkness. The inner rim is sharper where the wind presses harder. It is smoother where the outside medium is denser. Along the rim, thin striations run like brush marks following the curvature. The brush marks are regions of slightly different density and magnetic orientation. A payoff settles into that texture. A structured boundary can act like a lens. It can focus or defocus radio emission in subtle ways, changing apparent brightness without changing the source. A second concept enters and stays within the limit. Faraday rotation is the turning of polarization as radio waves pass through magnetized plasma. One sentence defines it. Two sentences keep it plain. A compass needle can rotate as it moves through a changing magnetic field. The needle does not create the field. It simply responds and turns. This matters because polarization rotation reveals the presence of magnetized plasma near the source and along the path. The main analogy stays unique and quiet. A thin curtain of beads can hang in a doorway. A breeze can make the beads twist and sway. A small bell passing behind the curtain is heard differently depending on how the beads are aligned. The sound is not changed at the source. The curtain shapes what arrives. In the same way, a nebula can twist the polarization and soften the time profile. Another visual scene follows the interior of the bubble. Inside, the plasma is not uniform. It forms sheets and filaments. Some filaments are long and thin. Some gather into knots. The knots have sharp leading edges and softer trailing tails like small comets made of density rather than dust. The sheets are flatter. They show a gentle gradient from dense to thin across their width. The radio shell of a burst passes through this interior. Each filament adds a small delay. Each knot adds a bit of scattering. The cumulative effect can be a noticeable tail on the received burst. A small payoff arrives in the cumulative nature. Many small irregularities can create a smooth tail. The tail is a record of turbulence even when no individual filament is resolved. A single number anchors the scale of the bubble without overloading the section. The nebula can span about 1 light year like a cavity. The size of the distance light travels in a year. This is vast compared with the magnetar itself. It is still small compared with a galaxy. The scale shift arrives gently. A star-sized object shapes a bubble larger than many star systems. That bubble then shapes signals that travel across intergalactic space. The origin is compact. The influence extends far. Another visual anchor forms where the bubble meets the outside medium. A thin shock-like front appears as a brighter arc. The arc is smooth in some regions. In other regions it is scalloped with shallow indentations like a softly serrated edge. The scalloping is a physical detail tied to instability at the boundary. A payoff settles into the scallops. An uneven boundary suggests mixing. Mixing brings fresh plasma into the bubble and changes turbulence levels. That can alter scattering from one epoch to another, even if the magnetar emission mechanism stays similar. The limit of observation enters softly and precisely. The bubble cannot be seen directly in most cases. It is inferred from radio properties and from how dispersion scattering and polarization rotation vary over time. Those variations can also come from other environments such as a dense star-forming region or a host galaxy's interstellar medium. Separating a local nebula from a distant contribution requires models and assumptions. It also requires repeated monitoring over long periods. This is a limit of indirect measurement and a limit of incomplete sampling. Another limit of intuition follows. A bubble suggests a stable container. In reality, the nebula can breathe and shift. Outflow changes can thicken the interior. Quiet intervals can allow settling and thinning. The boundary can drift. The internal filaments can rearrange. The nebula is a dynamic medium. Another payoff settles into that dynamism. Changing propagation effects can mimic changes in the source, so interpreting repetition patterns requires patience and cross-checks. A final visual scene closes the section with calm. The boundary arc dims slightly. The scalloped edge smooths as turbulence decays. Inside, filaments drift and dissolve into a more uniform haze. The bubble remains present as a faint structured cavity around the magnetar. The transition stays gentle. With a local nebula shaping signals, the next step is to place magnetars into a wider galactic setting and consider how often such environments occur and how their long lifetimes influence what kinds of transient signals appear across cosmic time. A magnetar can leave quiet footprints across its galaxy, even when it is not producing obvious bursts. The footprints appear as subtle changes in plasma structure and energetic particles that drift outward and persist. A slow scene opens in a calm region of a galaxy where the background is not empty. A faint interstellar haze fills the space between stars. Within it, a magnetar sits inside a dim cavity. The cavity is not symmetrical. One side is more rounded. The other side is flattened as if pressed by a denser external flow. Along the cavity wall, a thin rim glows faintly. The rim has a layered look. A brighter inner band hugs the boundary. A softer outer band fades away. The second sentence anchors the idea early. The long-term influence comes from repeated outflows and occasional flares that reshape nearby plasma. The first small clarity arrives with a gentle chain. A flare releases energy. Energy accelerates particles. Particles fill the surrounding region. Over time, the region becomes a persistent nebula-like cavity in a shell. This does not require constant violence. It requires only that outflows occur often enough to maintain structure. The first concept stays limited. Particle injection is the addition of energetic particles into a surrounding medium. One sentence defines it. 2 sentences return to imagery. A small drop of dye in water does not stay in one spot. It spreads into filaments and soft gradients. A second drop strengthens the colour in the same lanes. This matters because magnetar activity can keep a region energized and structured long after a single event. The visual anchor strengthens at the cavity wall. The wall is a boundary where density changes quickly. It looks like a thin membrane in space. Along the membrane, small scallops appear. Each scallop is a shallow indentation with a sharper inner edge and a softer outer fade. The scallops create a repeating pattern around the rim, but not perfectly evenly. Between scallops, the rim is smoother and thinner. The physical detail is the scalloped boundary and its layered bands. A payoff settles into that detail. A sharp density jump can act like a lens for radio waves and a reflector for particle streams. It can shape later bursts by adding extra scattering and polarization rotation when a signal passes near the rim. A second concept enters and stays within the limit. Synchrotron glow is radiation from fast particles spiraling in magnetic fields. One sentence defines it. 2 sentences keep it gentle. A thin wire carrying current can warm slightly and emit a faint glow in the dark. The glow is not a flame, it is a steady release of energy. This matters because an energized nebula can be present even when the magnetar is quiet in radio. Another slow scene moves inside the cavity. The interior is not uniform. It contains faint sheets of plasma. The sheets are like translucent curtains. They overlap and create regions of slightly higher density. Within the sheets, narrow filaments run along magnetic directions. The filaments twist gently. They create braided patterns that thicken in some places and thin in others. As energetic particles move through this interior, they follow the magnetic curves. They spiral and drift. The spiraling is not seen directly. It is inferred from the faint glow and from how radio signals would behave crossing the region. A payoff arrives within the braids. When magnetic structure is ordered, particles can remain confined longer. Confinement allows the nebula to persist. It also allows the boundary to stay sharp. The section then widens to a larger scale without adding new core concepts. The cavity does not remain isolated. It sits within a larger interstellar medium that has its own flows. Clouds drift past. Density changes with location. The cavity wall can be compressed on one side and relaxed on the other. This creates asymmetry. The asymmetry matters because signals leaving the magnetar can take different paths depending on direction. One direction crosses the thick rim. Another direction escapes through a thinner edge. Another payoff settles into that directional dependence. A burst can appear brighter or more smeared depending on which part of the cavity wall it crosses, even when the burst emission itself is similar. A single number anchors the time scale of persistence. The cavity can remain structured for about 10,000 years like a deep footprint in soft ground that stays visible long after the step. 10,000 years is long compared with a lifetime of bursts. It is short compared with galactic evolution. The scale shift arrives softly. 1,000th of a second burst leaves a trace that can influence the environment for thousands of years. The galaxy then carries that trace as part of its evolving fabric over millions of years. A limit of observation arrives gently and specifically. Such cavities and faint nebulae are difficult to detect directly. Their glow can be weak, their size can be small on the sky, their boundaries can blur into background emission. In many cases, only indirect signatures are accessible, such as variations in dispersion scattering and polarization in bursts. Even those variations can be explained by unrelated structures along the line of sight. This is a limit of contrast and a limit of resolving power. It is also a limit of separating cause from coincidence in a complex medium. A limit of intuition follows. The mind expects a clean bubble with a smooth wall. Real cavities are laced with filaments and gradients. Their edges are scalloped. Their interiors contain sheets and knots. The structure is not static. It drifts and mixes. Yet the overall cavity remains identifiable as a region of lower density and altered magnetization. Another payoff settles into that paradox. A messy medium can still have a stable signature when averaged over time and direction. A final visual scene closes the section with calm. The cavity rim continues to glow faintly along its layered bands. The scallops on the boundary soften slightly as turbulence relaxes. Inside, the braided filaments drift and thin. The cavity remains as a quiet footprint in the interstellar haze. The transition stays gentle and forward. With long-lived footprints in place, the next step is to follow how magnetars themselves age and change, and how a decaying magnetic field shifts the balance between frequent small outbursts and rarer large events across time. A magnetar does not keep the same temperament across time because its magnetic field slowly rearranges and loses energy. The changing field shifts what kinds of outbursts are likely and how the surroundings respond. A slow scene opens close to the magnetar surface in a region where the crust meets the magnetic stress. The surface is imagined as a dark sphere with a faint sheen. Across it, subtle bands appear like barely visible latitude lines. A few bands are brighter. Their edges are sharp on one side and blurred on the other. Between bands, a patchwork of dimmer regions forms. The patchwork has hairline cracks. The cracks are narrow, branching and uneven. They do not glow. They simply mark where strain concentrates. The second sentence anchors the idea early. Magnetic decay can move stress from one region to another and change the cadence of flares and quieter intervals. The first small clarity arrives in a calm rule. A magnetic field stores energy in its shape. When the shape changes, some energy converts into heat particle motion and radiation. The field does not need to vanish to matter. It only needs to relax gradually. The first concept stays limited. Magnetic decay is the gradual loss and rearrangement of magnetic energy. One sentence defines it. 2 sentences return to imagery. A twisted rope can unwind slowly. As it unwinds, tension migrates, and then releases in small slips. This matters because the magnetar can produce many small disturbances and rarer larger ones as the rope of field lines relaxes. A visual anchor forms around a bundle of field lines near the surface. The bundle looks like a bright loop rising from the sphere and returning nearby. Along the loop, brightness is not uniform. A thin ridge of higher intensity runs along the inner edge. The outer edge is softer with a faint halo. The loop's footpoints sit in 2 surface bands. The bands have sharp boundaries and gentle gradients across them. The physical detail is the loop ridge, the halo, and the sharp band edges at the footpoints. A payoff settles into that structure. Stress concentrates where field lines anchor. Those anchored regions become favoured sites for repeated small releases even as the overall field slowly weakens. A second concept enters and stays within the limit. Crustal yielding is the crust shifting when stress exceeds its support. 1 sentence defines it. 2 sentences keep it plain. A frozen lake can hold tension until a slow creep forms a new seam. The lake does not shatter everywhere. It yields along lines of weakness. This matters because small crustal shifts can jostle the magnetosphere and trigger bursts without requiring a single catastrophic event. Another slow scene moves outward to the magnetosphere. The loop bundle arches above the surface. Along it a thin plasma sheath clings like a translucent skin. The sheath has a thickness gradient. It is thicker near the footpoints. It thins toward the apex. When a small yielding event occurs, the loop brightness flickers. The ridge intensifies briefly. The halo thickens slightly. The sheath develops ripples that travel along the loop and then fade. A payoff arrives in the ripples. Even a small shift can reconfigure currents. Reconfigured currents can open a corridor for coherent radio emission or close it for a while. This makes outburst behavior age-dependent without making it predictable. A single number anchors the timescale of change. The strongest activity is often associated with the first 10,000 years, like a new spring that runs strongly before settling into a steadier trickle. 10,000 years is long compared with a flare. It is short compared with a galaxy's life. The scale shift arrives softly. A burst lasts less than a blink. The field evolves over thousands of years. The host galaxy remains for billions of years. Within that layered time, a magnetar can pass through phases. Early phases can be more active. Later phases can be quieter yet still capable of sudden releases. Another visual anchor forms at the boundary where closed lines end and open lines begin. The boundary is a ring like separatrix. It is not a rigid ring. It wobbles slightly as currents change. Its edges crisp in some sectors and blurred in others. The blur is caused by a thicker plasma sheath. The crisp sectors are clearer corridors. A payoff settles into that ring. As the field decays and rearranges, the location and openness of corridors can drift. A repeating source can change its repetition statistics over years. A non-repeating source can become weakly repeating, or become silent without a new object appearing. The limit of observation arrives gently and specifically. Aging cannot be watched directly on human timescales. Age is inferred from rotation, from environment, and from long-term monitoring. These inferences carry uncertainties. A magnetar can appear quiet simply because bursts are beamed away. A magnetar can appear active because the line of sight favours open corridors. The environment can mimic changes in the source. This is a limit of indirect age estimates and a limit of incomplete viewing geometry. A limit of intuition follows. The mind expects decay to be smooth and monotonic. Real systems can relax in steps. Stress can build quietly. and release intermittently. The average trend is downward. The moment-to-moment behaviour is uneven, yet the unevenness can still be part of a coherent aging story when viewed statistically across many sources. Another payoff settles into that perspective. A population of magnetars at different ages can explain why some bursts repeat often, some repeat rarely, and some appear as single flashes. A final scene closes the section with calm. The surface bands remain. The loop bridge softens slightly as currents relax. The hairline cracks on the surface remain faint with no sudden change. The ring-like boundary in the magnetosphere steadies. The system continues its slow drift toward lower stress. The transition stays gentle and forward, with aging and shifting activity in place. The final step is to gather the full arc into a quiet resolution where magnetars and their bursts fit into a stable cosmic landscape that settles into rest. In the far quiet parts of a galaxy, a magnetar's most dramatic moments become part of a wider and steadier pattern. The pattern is a simple one. Extreme fields create rare bursts, and the surrounding medium turns those bursts into the signals that travel. A slow scene opens at a distance where the magnetar is only a dim point. The surrounding space is not black. It holds a thin mist of plasma. The mist is uneven. It forms faint veils and clearer corridors. A broad arc of slightly denser material curves across the region like a pale shoreline. Along that shoreline, the density rises in a gentle gradient. The inner side is smoother. The outer side breaks into wisps. The second sentence anchors the idea early. The most important link is not a single flare. It is the full chain from field to burst to propagation through structured plasma. A first small clarity arrives with a calm separation. A magnetar produces energy by rearranging magnetic stress. The galaxy shapes that energy into what is finally received as a brief radio flash. These are distinct steps. Each step has its own limits and its own signatures. The first concept stays limited. Propagation is how a signal changes while travelling through matter. One sentence defines it. Two sentences return to everyday imagery. A bell rung in a foggy valley sounds different than a bell rung in dry air. The bell is the same. The path changes the sound. This matters because a fast radio burst can carry clues about both the source and the space it crosses. The visual anchor settles on the pale shoreline of plasma. A narrow band at its crest is brighter. Just behind it, a darker lane appears where density is lower. The boundary is thin. It is sharper than the interior. Fine ripples run along it. The ripples are shallow and slow. They make the boundary look like a calm tide line seen from above. A payoff arrives in that boundary. A thin, sharp gradient can add scattering and delay that depend on frequency, while a smoother interior adds only gentle dispersion. The boundary is where small structures matter. The interior is where averages matter. The second concept enters and stays within the limit. A dispersion measure is the total electron content along a path. One sentence defines it. Two sentences keep it simple. A path through thick smoke dims light more than a path through thin haze. The path length and density both matter. This matters because bursts can be compared across events to see whether the surrounding medium is changing. A slow scene moves closer still without human elements. The magnetar's neighbourhood is shown as layers. Near the source, a faint cavity remains. Farther out, the shoreline arc drifts and stretches. Between them, the plasma veils fold like translucent fabric. Some folds are aligned, others intersect. At the intersections, small knots appear. The knots are slightly brighter and slightly thicker. They act like tiny lenses. A signal would thread this maze. It would arrive with a characteristic width and a characteristic tail. Those features are not decoration. They are the path written into time. A payoff settles into that time writing. A burst that seems longer can be a short burst smeared by scattering. A burst that seems to repeat irregularly can be a regular engine filtered by changing corridors. A gentle scale shift arrives. In a fraction of a second, a burst passes. Over years, the surrounding plasma drifts and reorders. Over thousands of years, cavities and shells persist as quiet footprints. Over millions of years, a galaxy mixes its gas and smooths old edges. The burst is brief. The medium is patient. Another payoff arrives in that patience. Even when the engine fades with age, the environment can preserve a recognizable signature, like a faint trail remaining after the wind calms. A single number anchors the larger scale without straining precision. A spiral galaxy can be about 100,000 light-years across, like a wide city map, drawn in starlight, where the magnetar occupies a tiny corner. The magnetar's influence is local. The signal's journey is vast. This keeps the story balanced. The source is extreme. The galaxy is the stage that lets the extreme be noticed at all. The limit of observation arrives gently and specifically. Many parts of the chain cannot be separated cleanly. A burst spectrum can be shaped by the engine and by propagation. A polarization swing can reflect a changing magnetosphere or a changing screen along the path. Distance estimates can be uncertain when other plasma layers contribute. This is a limit of degeneracy. Different causes can produce similar observed patterns. It is also a limit of sampling. Only a small number of bursts are caught from any one source. Patterns can appear and vanish simply through sparse coverage. A limit of intuition follows. The mind expects one cause for one effect. Real signals carry layered causes. The cleanest answer is often a distribution of possibilities rather than a single mechanism. Yet calm progress is possible. Repetition statistics, frequency structure, and time delay trends can be combined. When they align, the chain becomes clearer. A payoff settles into that method. When the same source shows stable dispersion but changing scattering, the medium is likely shifting in small-scale structure rather than in total content. When dispersion drifts slowly over years, a broader environmental change is suggested. When polarization behavior changes quickly, the near-source region becomes the likely origin. A final slow scene closes the arc. The pale shoreline drifts onward. Its ripples smooth slightly. The cavity near the magnetar dims. The magnetar remains as a quiet point with occasional brief releases. The galaxy continues to breathe in slow flows and gradients. In that calm, the strongest field in the universe becomes a part of a broader quietness. The transition is a soft landing. The story does not need another mystery. It settles into the steady motion of plasma, the long patience of space, and the brief, clean flashes that pass and fade.